And this second portion, first portion, I really talk about the explosion. What's the shock wave when explosion occurs in the water, not in the air? So then at the time of explosion, then detonation wave is generated, and it propagates with roughly what speed? Charong, what speed? Detonation speed? Jongwon, what speed? Hassan? At the time of detonation, at the vicinity of the explosive, it starts exploding, and it generates the detonation wave at the beginning with extremely high temperature and high pressure, with the detonation speed which is about you know, how about Willie? Detonation speed. No, I said about 8,000 meters per second. You remember? I talked about 3 times already for that number. But that's okay if you okay, you could forget. Anybody could forget. So that's what I talk about it. So I'll just draw this is explosive. Explosive. This is in the water, of course. At the time of detonation, then this explosive is nothing but compacted compound of all different the chemicals, as we'll talk about that in a minute. And it generates the detonation speed in the vicinity here. At the beginning, of course, the shock wave, it will propagate in the radial directions. It generates a shock wave front, then it propagates so quick in radial direction. At the beginning, it generates a detonation, the wave front, with a tremendous speed, which is about 8,000 meters per second. So detonation speed is how much? About, remember, this is, I'm not asking to memorize it. It's a common sense. You don't have to memorize, just stick right here all the time. It's about 8,000 meters per second. Start compressing the water. Then it just slow down extremely fast. I can't tell you because I don't know, nobody knows when it really converges into acoustic speed, but it converges pretty fast. If you say the number, say the value, when it converges into the acoustic speed in the water, I could say less than 10 times within less than 10 times of radius of the explosive. Within that distance, it converges into the acoustic speed and propagate. I have a reason. In chapter 3, at the beginning of chapter 3, it shows, based on the experiment, So at the beginning, if I just write the right over here, the detonation speed gonna be something like goes really high, then converge down to acoustic speed. This is about 8,000 down to acoustic speed, which is about what? What's the acoustic speed in the water? Say 1500. So acoustic speed in the water, okay? In water. So it converges right down here, which is about the 1500, okay? 1500 meter per second, or 4,900 feet per second, or let's say 5,000 feet per second is all okay. But if you ask me, do I have to learn the English unit, U.S. gravitational unit? My answer is yes. You know, you deal with the metric, of course, SI unit, but in addition, when you go around the world to attend the conference, they deal with the U.S. gravitational system. Feet, second still, and pound. So it's nice to know. And what I do is, if I don't remember, a lot of conversion I don't remember. If you go into the internet, conversion of unit, then it shows all the tables. So that's what I look at it, okay? Converge right into it. The distance, it converges down to acoustic speed from detonation speed. Roughly, I can say at least about 10 times radius of, let's say, just R, which is initial explosive radius, okay? Within about 10 times. So all the experimental equations shown in chapter 3, maybe other chapters, is really valid after the 10 times of radius of initial explosive. So all the equations is kind of the valid within R. Initial radius of explosive is between roughly 10, well, this is not, what should I say, the distance, I'm going to just say maybe R, within 100 Ri. In this range, all the equation I'm providing is valid. You follow me? Don't misunderstand this. In the range, so from this is a 10 times Ri, all the equation I'm dealing with, shock pressure, maximum shock wave pressure, any quantity as you will say, impulse, whatever, as shown in chapter 3. Everything is in, this is I'm going to call over here R. Any parameter that I provide is good from 10 Ri to about 100 Ri. That's what I mean. You follow me? So then you could say, what should I do? What kind of the empirical relation should I use after the 100 Ri. Use the same. I don't have any other. So that's my answer. Okay. But as you learn this content underwater explosion, I want you to get the feel. Then you can really see that the direction and approach and some possible relations in addition to the experimental formulas and all that. That's what I try to drive at, to let you really determine rather than I keep providing all the informations. So that's one. And the shock wave is concerned at the beginning, at the time of detonations, then detonation wave has about 8,000 meter per second, and compressing the water, then the wave front is converging to about 1,500 meter per second, then it just proceed. That is called the really shock wave, okay? That's a shock wave. Initial shock wave or incident shock wave. Incident, word incident. So this is a source. Then this shock wave front is moving in the radial direction. So think this shock wave front by conventional explosive, you can say it's paper thin. You can say it's paper thin shock wave. If I say a submarine is sitting right here, it's going to just pass the one particular section to the other. The shock wave front by nuclear explosion is going to take a certain range. It's a shock wave front is a thing. We're not dealing with nuclear explosion in this course. It's just by the conventional explosion. Okay. Then shock wave will go. 1,500 meter per second is pretty fast. Think about running, in a second, bang, 1 second. You run 1,500 meter, fast, isn't it? Then what happened? And this is a charge, and I'm going to draw this charge right here. This is a charge. Then shock wave. This is a wave front. Shock wave. This is a shock wave. Wave front is just gone. But inside here, of course, you have initial explosive after bang. But this energy is here still. Energy is still not only here, some carried by the shock wave. Shock wave, this is not absolute value. About 53% of total energy is carried by the shock wave. By the shock wave front contains the pressure. Is a pressure wave. Shock wave is a pressure wave. Then it contains about the 50 roughly, okay? Could be 51, could be 55, roughly average 53% of the total energy carried by this. Then still all that the black powder done as a result of explosion is still there. It carries energy. how many percent? The remaining energy is 47%. Sangwon and Yongwon, you can hear, right? My voice?
Yes.
So you can see the blackboard? Maybe not. Oh, you cannot see the blackboard well. That's okay, because everything I'm doing is in the handout, and also if you listen to my talk, that's about all you need. Okay, so 47% of energy is contained, is trapped inside the gas, explosive gas product, okay, as a result of explosion. Then it's confined by the water. It's confined by the water. So it has energy in there, then it will slowly grow. It's called the gas bubble. It's called the gas bubble. Okay? It's called the gas bubble. Gas bubble. Or some people call bubble. Same thing. So that gas bubble grow, of course. So as a gas bubble grow, it's going to grow forever? Gas bubble is going to grow forever? Willie said no. So is it going to stop after for a while? Why? Explosion occurs, as Willie said, explosion occurs at a certain depth of the water, right? From the free surface, could it be could it be 10 meter below, 20 meter below, or 100 meter below? Then detonation occurs there. So it grows. So as it grows, then the gas bubble pressure is keep growing or reducing. Gas bubble pressure, right, at the surface of the gas bubble, is it growing? Reducing, because surface area is growing, right? Then it's reducing. Then it's keep reducing. And when the growth gonna stop? When? It's gonna, gas bubble gonna keep growing. When it's gonna stop? It's gonna grow forever? No. Willie said it's gonna grow until the surface pressure matches with hydrostatic pressure plus atmospheric pressure, right? It's a constant, right? Atmospheric pressure plus hydrostatic pressure. Then bubble growth stops. Is it going to stop right away? No, it's not. Why? Inertia. When you drive a freeway, when you drive a highway, you drive the 100 kilometer per hour, boom, and suddenly another car cut right in front of you, then you have to push the brake, right? If you push the brake, can you stop the car right there? No, because you have inertia force right on the car, which means mass of the car times accelerations, G there. I'm sorry, A there. So it has inertial force. It's going to skid, boom, right? So it's going to go some additional distance. in general sense, for the physics. So then it stops. At the meantime, Gusto, you think of something else. Right? No? Yeah, you have to try because you're late. But anyway, then, listen carefully, as it grows in the water, then that energy start to dissipate into the water, right? Not everything in one shot. It slowly dissipate. Energy contained in the gas is radiate into the water. Okay? So bubble start to losing the energy, right? Makes sense, right? Then it stops, the growth of gas bubble stops, then it starts contracting, right? Because lots of energy get lost in the water, just to radiate into the water. So total energy is reduced, then bubble get down to contracting, right? Contracting and contracting. When it get down to the minimum, then what happened? Look, this is a minimum bubble, whatever that is. Then if you look at the gas bubble, pressure at the top, consider pressure at the top and pressure at the bottom with a simple theory. Which is higher? Top or bottom? Bottom is higher. So you have the bottom pressure is pushing the bubble upward direction. Net pressure is pushing is upward direction. As it pushing, then it lost the balance. It lost the balance, then what happened? Then bubble collapses. In the water, as something collapses, it generates the secondary shock. Okay? But it's all the gas powder is still confined in the water, goes nowhere. After it loses the balance, then what happened? It's still there, then gas bubble grow again. Not to the same size of initial gas bubble, because lost energy in the water. And the second gas bubble oscillation size is smaller. And third gas bubble size is getting smaller and smaller. Then is it going to stay down in the water and oscillate down there? No. When you go down, for snorkeling or a lot of leisure diving, people enjoy it. When they go down in the water, then they stay there forever? No. They have to come back to the water surface. You have to breathe, right? Nature is all same. Explosion is going to migrate toward the free surface as it oscillates. As it oscillates, they have to breathe, simply speaking. That's a natural law. Well, by the gas bubble, migrate means move toward the free surface. Why? Because by the what force? Buoyancy force. Right? Gas bubble. It has buoyancy force. What's the buoyancy force? How do you compute the buoyancy force? The gas, the volume, times what? Mass density of the water multiply G, right? The equivalent weight of the water contained for the volume of the gas bubble. So it just pushes up. As it oscillates, it's going to keep pushing. Then it's going to come near the free surface. Then free surface is governed by atmospheric pressure, which is 1 bar, or 14.7 psi, pound per inch square. Take a look at conversion factor. You go look at it. Conversion factor into megapascal. 1 bar is 14.7 psi. Is right. When it tried to come out to the atmosphere, the atmosphere said, "Hey, don't come. That's my territory. You stay down." That's what the real nature struggle for survivability. So when the bubble rises toward the free surface, the atmospheric pressure keep tapping, "Hey, stay there." That's what happened. Then it doesn't come out quickly, but atmospheric pressure keeps saying, "Stay down, stay down." Then it just generates a little bit murmuring, "Oh, this is not my territory. Oh, I can't go up." Then when it really grows, the buoyancy force is so high, then it just pops right out. Then you see the plumes, right? That's what happened. Oscillation looks nothing but very important for naval ship design. Very, very important. That's what I want you to read. I can't erase this well. Anyway. Who controls this? This is what I wrote down here. I want you to read. So I gave you all the basic phenomena, and I want you to read all this, okay? And the combustion, detonation, I have done it. And misfires and all that, I have done it. But now I'm going to doing here. There are two different types of explosive. One is pure explosive. Another one is explosive mixture. Or sometimes some people call this as high explosive. Two different types, okay? So one is what? Pure explosive. Two different types. Pure explosive. It's really pure. When I say pure, it's a grain is purely one kind of molecular. When this is one type, pure explosive. Another type is explosive mixture. Or a lot of people call this as high explosive, like a TNT. Okay? High explosive. And the pure explosive, as you see in your write-up, take a look at your write-up, it said it is a single chemical substance. Single chemical substance. pure explosive is very, very unstable. If you don't handle properly, it will explode right there. You have to really care to handle this. You need a certificate to handle, otherwise you can't touch it. Any explosive without the certificate, you can't touch it. But the pure explosive, very sensitive. Explosive mixture is not as sensitive as pure explosive, like a TNT. Okay, like a TNT. So when you make a bomb, but explosive mixture or high explosive is a mixture of all different kind of the substances, all different kind of a grain. If you look at the pure explosive, that is usually white, one substance. But high explosive is a combination of all different mixture, so it's a different color. It's not the one color. It's a mixture of the grain, okay? But it has a different personality. What personality is showing right there? If you look at the page 2.1-6 out there, I can display here. But if you look at there, for the pure explosive, primary explosive, it's all same thing. Pure explosive, primary explosive is all same. Okay? It's all same. But if you look at the detonation speed, what's the detonation speed for high explosive? Can you read? Which is about 1300 feet per second. Okay? What about the high explosive? TNT 22,000 and RDX 26,800, COM B or HBX1, pentolite. This is all around the 25,000. Tetriol, PTN is all in that range, about 22,000 to 26,000 feet per second. As you look at here, which has a higher the detonation speed? This is detonation speed. Primary explosive or pure explosive or high explosive, which is higher detonation speed? High explosive has higher detonation speed. But if you look at the detonation heat, last column in page 6, last column, the detonation heat, which is higher? The high explosive is higher. But as you look at the density there, which is higher? Primary explosive or pure explosive is higher. So if you're going to look at the basic bomb, as you look at the basic bomb, can you switch it there, the notes? If you look at the basic bomb there, as you look at here, this is very primitive, the bomb design, but this is it. Okay. This is outer shell. It's a cylinder, right? And this is called the booster is in there. And if you look at the booster, there is a detonator right at here, and you put the wire right in. So when you detonate, this detonator will explode first. Right here you have primary or pure explosive is in there. And in outside you have another casing in there, cylinder, which is called the booster. When you confine the volume, then what happens? It generates higher power, right? So when it starts to explosion occurs here, detonation speed for a pure explosive is slower, right? Slower than high explosive, right? So it's going to spread pretty uniformly, then goes into the inside of the booster, and that's high explosive, and then you start to move much faster, then get outside here, it has high explosive, then it just all the casing shelter or the shattering away, which is called the fragment. That's the situations, okay? So you can see that the pure explosive is kind of an example for the bomb design. Of course, nowadays there is a laser, use of the lasers and all control devices it has. And basics over here is explosive is primary, very sensitive, high explosive. When I say insensitive, you can just throw the high explosive, throw away. You can't do that. Of course it will, but relative comparison between the primary explosive and high explosive, compared to these two, this is rather insensitive, okay? And the low detonation speed, high detonation speed, low power generated, high power generated, relatively speaking, that's what I mean. Both are all in the category of explosive. But compare both, then such a thing you can say about it. And nuclear explosion you can read, but I'll just pass. Yeah.
What is the booster function? Why use booster in design? Can we use booster?
Why use a booster? Booster. Yeah. Okay. Why use a booster? So here I'm going to just read through here. If you say just the detonator right there, this is a casing, okay? If you put the detonator, then you have a pin right here. When it explodes, of course it will explode. And the detonation, when detonation occurs, then a detonation wave will propagate, eventually broke this out. Okay? So you could make the bomb like this, but which is less effective. Why? If you put the booster in right here, around there, when it explodes, detonator, low detonation speed compared to high explosive. So it will, detonation wave will propagate, and when it confine the volume, then what happened? It generates more power. When you confine the volume, it generates more power. The way it propagates the power is much stronger than without the booster. As the name says, booster, it's boosting up the power. Bullet. And you put the bullet in there, in the casing. If you don't have a casing, not that powerful. Because of the casing, then you have a gunpowder inside the casing, then it generates the confinement of the gunpowder, then it really pushes the bullet out with really high speed. I'm not in the position to teach the bombs or bullets, but in the process of explaining the underwater explosion, this is what happened. So as an example, then it just to power, just to move fast, then it break all the shell casing. Okay? Yeah. And some more shock wave. I was going to show about Dongman. How many minutes? 15. 15? 15 minutes? 1-5? U571, the movie clip Dongman brought in, I asked him yesterday, the day before yesterday, to show you the depth charge and all that, but we have 10:45. Maybe we'll move to other time. Dongman. So maybe next after we come back from Chuseok, when I give a 2-hour talk, then maybe that time we can show 15 minutes. Okay, let's do that. Yeah, it's very interesting segment of U571. Okay, here more to get you the more on shock wave. This is a charge location, and at 5 feet away. 5 feet away. 5 feet is 1 meter is about 3.3. 1 meter is 3.3 feet. So you can imagine, okay? It's about 5 feet, which is about 1.67 meters away. Then this is a 300-pound TNT. I want you to convert. This is converted to kilogram. You have to divide by this by 2.2, roughly. Then about 140 kilogram TNT. So 34,000 psi, tremendous. But about 45 feet away is about 10 times less. It's really coming down fast, right? 50 feet away, 2,200. 500 feet away, it's 5 feet, 34,000. 500 feet away, 160. It just goes exponential decay. It's really proportional to 1 over d, but it's come really down fast, okay? Shock wave, conventional shock wave. I mentioned not the nuclear shock wave, but we are not dealing with the nuclear. So get the feel of it. And this is a discontinuous, the wave front. It's a flat. And it has a trail there. See, trail. It has a trail. That means here, if this is 2,200 psi, this could be 2,000, 1,800. Is gradually decaying. Okay? Pressure profile is proportional to 1 over d. So proportional to 1 over d. As it going down, it's just moving down, not like a nearly exponential decay, but not like exactly exponential. So just to get you feel of it, okay? And for 20 at the 50 feet away, so which means 50 feet away. Do we have a 50 feet? It's this. This is a shock wave is moving along the distance here, but this, I'm sitting right here at 50 feet away, then see how the shock wave passing me. So which is really time versus the shock wave pressure. So it's exponential decay. Comes straight down, okay? Of course, we're going to deal with the equations pretty soon. But first to get all the physics part of it. Then the reason I'm really spending on the physics part of it is later it's much easier. Then I don't have to re-explain. Then your logic would be very straightforward. But if you mix it here, then you will mix up forever. But if you measure the shock wave pressure, very strange phenomena is happening. This is 500 feet away. Of course, its maximum pressure is 160 psi. Then it exponentially decay is supposed to come like that. But it doesn't do that. In actual measurement, what happened is as it coming down here, then suddenly the pressure is cut and go down slightly below zero and murmuring around and could have another small peak which is much wider than that peak. Like this is really up, but here is much wider and down. Then this is called the surface cutoff. It's a free surface cutoff. I'll spend some time on this. Very important phenomena. I said this is due to the surface reflection wave. The surface reflection wave is sometimes called the rarefaction wave, or sometimes it's called the tension wave. That's the very important nature. When the shock wave hit the free surface, okay, then of course it will generate the reflection wave from the free surface. And the fluid particle or a particle will kick in what direction? Toward the air direction. Keep moving in air direction, but shock wave is moving toward the water. So what happened is water particle is moving the opposite to the direction of the shock wave.